The schematic presented here represents the flow of visualization of data or information. It is particularly influenced by the work of French cartographer Jacques Bertin, who devised an entire system of intelligent data visualization documented in his 1967 book entitled Semiologie graphique, or in English, The Semiology of Graphics. The idea here is that we have some data and analyze that data as a first step. We then decide on the best representation of information. We then map the components of the data to answer our or our audience's question in a way that is readily comprehensible and persuasive. While this is generally the system for data visualization, we might sometimes want to reverse or flip that process or cycle through these stages. If, for example, we think about big data and the huge volumes of data that we might be analyzing sometimes, it's not actually possible to know what to ask of the data. Sometimes visual exploration is actually a very useful tool for helping us understand what questions we should be asking of the data in the first place. It's also perfectly fine to work in the opposite direction, to come up with some visualizations that help us represent information in our data set to see whether it shows us if there are any good questions that we could ask. Nevertheless, this section of the course will, for the most part, be consistent with the process as illustrated, focusing in particular on how to communicate information for easy comprehension. Here we introduce some terms we'll be using that originate in the work of Bertin. The content will be the information that we want to communicate, and the container is the graphic system, the ways in which we design and present that information. While the container is a design, an intervention used to present the data, it needs to be true to the content to protect the veracity of the data. Sometimes the most beautiful data representations are meaningful, and sometimes they just distort the data for the sake of good graphics. We're certainly about making good graphics, but we never distort the data. The invariant is the data or information that we are going to present, and the component is a variable, which will be basically how we choose to represent that underlying information. There are, of course, lots of different variations for representing the data available. We are going to be learning about something called the visual variables that are the building blocks of any graphic science system. We're also going to take into account the planar dimensions of the data, often referred to as axes, as they present the essential two-dimensional context for data interpretation. As always, we're dealing with data, so we have to think about the data type. Is it qualitative? Is it quantitative? And in which ways would these various data types be better presented? These considerations are termed component organization. We can use this small data set with information on cars presented in tabular form to illustrate some of these points. The first columns show the kind of transmission, automatic or manual, including the number of gears. The second column shows the class of vehicle, and the third shows the engine size. We start by determining the invariant and the components. Recall that the invariant is the information to be presented, and the component or variables will be the various ways we can present that information. In this case, our invariant is all the vehicle information in the data set. We could present, among other things, the average fuel efficiency based on each car line class, so we can compare fuel efficiencies of compact cars to large pickups. We might want to break this down further by the number of gears a car has or its transmission type, posing a question such as, are automatics more fuel efficient than manual cars? We can compare across whatever variables are available. Each component is then represented by a sign a symbolic mark that represents the component in the visualization. Usually this will be displayed in 2D using the graphic planar variables or positions on the horizontal and vertical axes, also known as the X and Y axes. 3D graphics might on occasion be suitable for representing some data, but should be used sparingly. The components are then rendered via the retinal variables, or the visual properties of the mark, including color, shape, texture, and size. We will go into some detail regarding the retinal variables in the next concept video. The planar and retinal variables together form the visual variables. Burton argued that our graphics, in order to communicate, required the visual variables to be at least equal to the number of components that we are trying to represent. Otherwise, we don't have a large enough system to represent the maximum set of information. In addition, he claimed that human perception was well equipped to handle 3 components, but anything more than 3 components is not easily perceived by our visual system. We really need to carefully construct efficient graphics so that we can still communicate meaning with large numbers of components. In order to construct information meaningfully, we have to think about the data that the components represent. 2 broad distinctions are important here. Data can be qualitative or quantitative. The table here consists of qualitative categorical data, where the categories represent the information, which can be either nominal or ordinal. With nominal data, such as whether a car transmission is automatic or manual, the order does not imply anything. Ordinal data, on the other hand, has the potential to be ranked. The car line class could allow us to compare differences between engine size. Of course, quantitative data can also represent a ratio where there is an absolute zero and direct comparisons, such as 4 kilos is twice the weight as 2 kilos, are possible. In the following slides, and indeed the following concept videos, we will refer to quantitative components without making the distinction between interval and ratio data. So, how do we organize nominal, ordinal, and quantitative information? With nominal information, we can try to differentiate between values. Is a value similar to or different from another value? In the example here, we could try to compare and contrast the transmission type, perhaps suggesting that the Auto S6 is similar to, say, the Auto A5. The nice thing about nominal components is that because there is no natural ranking involved, we can reorder the categories to see if we can reveal a pattern. On the other hand, if our data are ordinal, then the data is ordered, so we can't reorder the components at will. We have to maintain the order after the original data set. So here, no matter how we would visualize the car line class, we would have to keep that ordering from subcompact through to pickup 4-wheel drive. Now, we could reverse the ordering so you could start with the largest and end with the smallest, but we wouldn't play around with anything in between. Quantitative components present a lot of possibilities for organization. We can use them to reveal information, to distinguish, and to compare. The length of components is another important concept. Length depends on the variable type. For example, if we look at the car line class here, it says that the length is equal to 5. That's because there are different categories, and when tabulated, they come to 5. On the other hand, if you've got continuous numbers, there is no length available. So we don't typically think about lengths with numbers. This might seem a bit counterintuitive, but remember, it's about how many groupings or how many classes we can divide our data into. There is an exception to this. We can determine length from numerical data if we create categories for that data. A good example would be age. So, even though ages are not in themselves categorical, we might nominate age bands or groups, such as 0 to 20, 20 to 40, 40 to 60, and so on. When we speak of lengths, we might also be concerned with whether they are short or long. If you hear about a short length for a component, it means there are less than 4 categories. A long length for our component would mean it has more than 15 categories. There are 3 main stages for reading a graphic. The graphics here use the data from the previous slide, and you can see that we've got fuel efficiency on the y-axis and we've got the car line on the x-axis. This is what's called external identification. We're starting from the outside of the graphic and we will move from the outside edge inwards to gain understanding. Now typically the brain does this incredibly quickly, but we're slowing down the process on this slide so you can see how the human brain does in an instant. That's stage 1. Stage 2 moves to what is called internal identification. Here we answer the question of how to represent this information. Dow mapped the car line to the horizontal axes and fuel efficiency to the vertical axes. Do we even use these sorts of axes, or do we use a different style of representation? The final stage, stage 3, is about how we understand the marks. These marks could be points, lines, or areas. In this case, we've got points. So how we perceive the marks that represent the information and what's communicated to us based on how these marks, as they are placed across the 2 planar dimensions, is the concern of stage 3. These are the 3 stages of reading an image. Our brain goes from external identification towards the internal part of the graphic, and then it tries to attach meaning to what it's looking at. And this is what we should cater for when we create graphics.